Hi guys, my name is Vinay Jain and today we're going to talk about some dry run examples for better understanding of depth first search algorithm using stacks. So a brief overview of algorithm DFS using stacks is you create an empty stack and visited set. The stack is used for pushing all the nodes onto the stack to implement depth first search approach, and visited set is to keep track of all the nodes that have been visited so that we do not visit them again. So as long as the stack is not empty, as long as there is some node in the stack to be iterated, we pop the topmost node in the stack and check whether that pop node is equal to the value that we're looking for or not. If it isn't, then we proceed further and add the child nodes if they exist or the current node to the stack and add the pop node to the visited set, and we keep on iterating in this fashion as long as either the stack is not empty or we don't find our target that we're looking for. So this is the approach that we use for a binary tree, that is a tree with maximum in which every node has zero nodes, zero child nodes, one child node, or maximum two child nodes. The time complexity for this algorithm is O of V plus E, and space complexity is big O of V, where V stands for vertices count and E stands for edges count. So now let's proceed to the dry run examples that I was talking about. So these are the dry run examples here for DFS algorithm using stacks. So let's say we have a tree like this and the root of the tree is node 1 and we're looking for node 1. So as per our algorithm, what do? We have a stack, right? So let's say this is our stack and this is our pop node, right? This is our stack and we have our visited set as well. So what do we do first? We first put the root node onto the stack. Now once we do that, then we operate our algorithm, which is pop the topmost node in the stack to pop node, assign it to pop node, check whether this is the value that we're looking for or not. Yes, it is. So we have found what we are looking for. So now that we have found what we're looking for, we stop our algorithm, return true, and that's it. That is for this algorithm. We proceed to the next example. So again, we have a stack. This is our stack and this is our pop node and our visited set. So let's start from the root of the tree, which is node 1. Push the root of the tree onto the stack. Now this is where our iterative algorithm starts. We pop the topmost node in the stack and assign it to pop node. Check whether that is the target that we're looking for or not. 1 is not equal to 5. So we add its right child to the stack first and then the left child. The right child is 2, so we add that to the stack, 2. And the left child is null because we do not have anything here, right? So we don't add anything. We add now the pop node to the visited set, signifying that it has been visited. So adding node 2, the right child, to the stack essentially means that we've traversed this in this fashion, in the next depth in this fashion. Now we pop the next topmost node in the stack, which is node 2. So we pop it, assign it to pop node, check for whether it's its target or not. It's not the target, right? So we add its children to the stack. First we add the right child, then we add the left child, which is node 4. So essentially this means that we have now traversed in this fashion. Now that we have done this, add node 2 to the visited set, signifying that it has been visited now. Next we pop the node 4 from the top of the stack, which is this part. So we assign it to pop node and check for its target, whether it's equal to target or not. It's not equal to target, so we add its children to the stack. We do not have a right child, we only have a left child, so we add 5 to the stack and add 4 to the visited set. So this essentially means now we have completed exploring this path. This path has been explored, this path has been explored. I'll remove these arrows. Now that we have done this, push the next node that is on the top of the stack, which is node 5. Push it, pop it, and assign it to pop node. Check for its target, whether it's equal to our target or not. Yes, it is. So we have found our match in the tree, and therefore we return this. Since we have found our match, we return true. So this is it for this example. Now let's do another example. Let's say this is the example that we have, and we're looking for target 7 in this tree. So how does this work? So again, we have a stack and we have our pop node and the visited set. So we push the root node onto the stack first and then begin our algorithm. Pop the topmost node in the stack, assign it to pop node, check whether it's equal to our target or not. It is not. Target is 7 and the current node that we have is node 1. So we don't do anything. Add the right child to the stack first and then the left child. Now that we have worked with the children, add the pop node to the visited set. That means this node has been visited. Next, we pop the topmost node in the stack, which is node 2, assign it to pop node, and see if it's our target or not. It is not, so we add its children to the stack. So we add node 4, right child first, and then the left child, node 3. Once that is done, we add it to the visited set, signifying that this path has now been explored. Next, we pop the topmost node in the stack, which is node 3. So we pop node 3, assign it to pop node, and check for its children. Does it have any children? Is it equal to our target or not? No, it is not. So we check for its children. It doesn't have any children, so we don't add anything to the stack. We just add it to our visited set, signifying that this path has now been visited. Notice that again, this is the tree is being searched and traversed in a depth first approach. Next, we pop the topmost node in the stack, which is node 4, assign it to pop node. Check whether node 4 is our target or not. It is not. And what about its children? It doesn't have any children, so we add merely to our visited set, signifying that this part has now been explored. Now, next we pop the topmost node in the stack, which is node 5. Check for node 5 is our target or not. It is not. So we add its children to our stack. Node 5 children, our right child is 6 and it doesn't have a left child. So we don't add anything to the stack. We just add now the, my bad, 5 should have been added to the visited set. We just now add, my bad, we just now add node 6 to the stack and node 5 now to the visited set, signifying that this has been visited. Next, we're working with whatever is on the top of the stack. So we pop that, which is node 6 now. We check for node 6 whether it's our target or not. No, it is not. So we add its children to the stack. It has only one child, right child. So we add that, node 7, and then add node 6 to the visited set, signifying that this node has been explored and now this path has been explored. Once that is done, we pop the next topmost node on the stack, which is node 7, assign it to pop node, check if it's our target or not. Yes, it is. So we have found our result and we now return true. So this is how the algorithm works in this case. Let's try one more example where we have a tree like this. We have a stack to help us imitate depth first search approach, pop node to keep track of the current node that we're working with, and visited set to keep track of what nodes have we visited so far. So we push the root node onto the stack and begin our algorithm. Pop the topmost node in the stack, assign it to pop node, check if it's our target or not. It is not. For the moment, let's assume that the target that we're looking for is 7. Let's say this is the target that we're looking for. So again, back to our algorithm, we check whether pop node is our target or not. No, it is not. So we pushes children to the stack. So we push the right child first, which is 6, and left child then after that, so which is node 2. Add one node to our visited set, signifying that this part has been visited. Now pop the topmost node in the stack, which is node 2, assign it to pop node, check if it's a target or not. It is not. So add its children to the stack. It only has one child, node 3, so we add that to the stack, and then add node 2 to the visited set, signifying that this depth has been visited in this order. Pop the topmost node in the stack, assign it to pop node, check if it's a target or not. No, it's not. Assign it to the visited set, but before doing that, check its children. Do we have children for node 3? Yes, we do. We only have one child, right child. We add it to the stack, and then add pop node to the visited set, signifying that this depth in this order has now been visited. Next, pop the topmost node in the stack, node 4, assign it to pop node, check if it's a target or not. No, it's not. Add its children to the stack. So now we add node 5 to the stack and add node 4 to the visited set. Now that we have added node 4 to the visited set, that means we have traversed this depth now in this order. Pop the topmost node in the stack, node 5 is assigned to pop node. Check if it's a target or not. No, it's not a target. And add the nodes 5 children to the stack. Node 5 does not have any children, right? It is all null. So we don't add anything to the stack. We just add this to our visited set. That means we have iterated this section now, this depth, and then we go back to popping the node from the stack, the topmost node in the stack, which is now node 6. So we pop that node, assign it to pop node. Is this our target? No, it is not. So we add its children to the stack. Node 6 doesn't have any children, right? So we just add it to our visited set, signifying that this part has now been visited. This depth has now been visited, and then we return. Now we check whether the stack is empty or not. The stack is empty, right? So this means that we have iterated the complete tree, but we have not found anything yet. So now not found it, return false, signifying that the node that we're looking for doesn't simply exist in the tree. I hope these examples help you understand the algorithm better.